Good afternoon, everyone. My name is Martin LeClerc. It's a great honor for me being here representing Polytechnique, Montreal. The title of my presentation is Multi-Directional Hybrid Simulation Test at Polytechnique, Montreal. I present the system, the challenges, and the application that we have done in the last year. Here's the plan of my presentation. I'll first talk about our MDHTS. We don't call it a mass system, to be honest. We call it MDHTS. I did not choose the name. Professor Tremblay did, okay? But it's not very easy to pronounce, but it stands for Multi-Directional Hybrid Testing System. And I'll proceed then with my presentation with the challenges. I'll talk about the stiffness of the system, the friction, which is the most problematic thing that we encounter, and the measurement precision when you're testing very stiff specimen. I'll present you two applications and then end up my presentation with conclusions. So Polytechnique Montreal looks like this. We have many features. We have, I'll explain everything into international metric units, but the strong floor is pretty much 640 square meter, around 7,000 square feet. We have a strong reaction wall made of L shape. It's 10 meter high, 12 meter in width in both directions. And we're using that strong wall to resist our multi-axis system, which is composed of 8 actuators, and I'll explain that a bit later. We have 2.6 million pounds or 12 meganewton load frame that can go either in compression or in tension. It can go dynamic as well, up to 4 Hertz if you want to do fatigue test. We have an instrument machine, so we not only have MTS system, we do have a lot of MTS, but we do have an instrument machine. Here, it's a 2.5 meganewton system. And we have a uniaxial shake table, which is an MTS system. So here's the MDHTS. I'll call it a mast. Okay, so it's going to be easier for everyone. So pretty much it's a 6 degree of freedom system. It's as you can see it here. The lab right now, as you see it, it's pretty much clean. So I was surprised when I visited the lab here that there was nothing. It was on the floor. It was pretty much clean. Normally a lab doesn't look like this, okay? And this was pretty much for a picture as well, so we cleaned up everything up. But if you look right now, if you would have a look at our lab, it's not really the case right now. So the manufacturer is MTS Corporation. It's a full degree of system, full 6 degree of system. It has a mixed mode of displacement and force. We can do quasi-static, pseudodynamic, and hybrid testing. We have 2 types of displacement feedback signals. One is absolute referencing. This is coming from the LVDTs within the actuators, and we ask MTS to make a relative referencing. So pretty much we add up 8 encoders, so we can only measure the local displacement of the specimen itself. So when you're doing hybrid, this is mandatory. We have 2 hybrid configuration possible. Pretty much we're using the CSI from MTS right now, but we do have a real-time machine that is hooked up to the system. The total capacity, so pretty much we have 8 actuators. The 4 vertical actuators, they are single-ended, so they can go more higher in terms of force in compression. But we maintain that as pretty much as the limit in the tension direction. So it's 4 times 1800 kilonewton. We have in both directions 2 horizontal actuators. They are double-ended, so dynamic actuators, and they go up to 1000 kilonewton each, which is about 220 kips, in fact. We have a vertical amplitude of plus and minus 300 millimeter, and a horizontal displacement of plus and minus 375 millimeters. We have a huge capacity and moments depending if you put the platen higher or lower into the different configuration. Okay, I'll switch now to the challenges that we are facing. So we were aware that if you test using only the displacement coming from the actuator, so the absolute referencing, and you take that into account that this will represent the displacement that would be imposed on your specimen, then you're completely out of the track. You need to really control your system within the displacement of your specimen only, not from the absolute referencing. and we did a lot of analysis here. This is showing a SAP model, SAP 2000 model, just to show you. If we test somehow a very stiff specimen inside the platen does deform. The main objective here was to get the most stiffness out of the system. The other two masks known right now, which one is in Minneapolis and the other one in Melbourne, they are cruciform shape. Ours is pretty much a caisson type, so it's pretty much a rectangular shape. We wanted to have the system as stiff as possible. We don't want to have much elastic energy accumulated into that system. We also did very, very refined finite element analysis using abacus. We designed a lot of anchoring plates, as you can see here. So I want to make sure that we only break the specimen, we don't break the anchorage or anything like that. Unfortunately, we yielded 2 anchor bars into our big 12 meganewton press, and you can imagine that it's impossible to remove. So you only have to cut those bars, and if you want to restore the threaded part there, you have to machine it. Okay. So pretty much what we did was just only cut the bars from there. So we didn't want to repeat this problematic. So we just make sure that the finite element was pretty much capturing all the effects that would happen in the lab. So the relative system that we use now to control our hybrid testing is pretty much composed of 8 transducers. It's 4 triangulation. These 4 each triangulation is composed of 1 vertical transducer and 1 diagonal transducer. And it's disposed all around the specimen, so in each of the faces. So it pretty much captures only the displacement of the system. That way, you don't introduce into your control loop any deformation that would come outside of from the system itself. Because if you're controlling with the absolute referencing, you put energy into the control loop, and if you have somehow a brittle behavior during your test, so if your rebar is breaking, then you're going to have a relaxation of that system here, and it's going to impose an additional displacement you won't capture, and probably you're going to end up having more damage imposed to that relaxation. So we decided to go with a relative system like this, and it does the job perfectly. The problem is that when you have such a big machine, is that you have to reference this in a 3D manner. So you have to locate the pin that is coming out exactly here, and there's a hook as well on top here, which is about 4 meter or 5 meter high in the air. So you don't take your measuring tape to locate those. You need to be very, very, very precise. So we use metrology grade scanners to locate them. Trying to avoid as much as possible the errors that were presented today. Now let's address the friction problem. We've been working on these problems for a while, so I'll ask you to listen carefully. Okay, I have a small video here. So I'm going to show you pretty much the first hybrid test we did. This is going to bring old memories to Sean. He was there in the lab. So we pretty much did a first hybrid test that was like almost 3 years ago. It was a 3DOF, so we had the 2 translational movements and the rotational around the x-axis. And when we started the test, this is what happened. Oops, sorry, coming back. If you can pay attention to the screen here moving, so the whole system was pretty much rocking in all directions, going sideways, up and down, rotating. You should have seen the look on Sean's face at that time. Okay, so as you can see, there was no really stable control onto this, so I'll explain to you what is happening here. So pretty much when you start the finite element hybrid simulation, you impose a displacement to your platen. So pretty much at the first time step, the finite element models compute the displacement, send that to the controller imposed that displacement, and the feedback of the forces are sent back to the finite element model, and then you can proceed with the next iteration. But what is happening here, the feedback of the system is composed of 2 major things. One is the specimen response, which is quite small because the time step is very, very low. So the imposed displacement is quite very, very small. But the friction response is quite high here. So what you end up having, instead of having this kind of behavior, which is the specimen expected response, you get a huge level of force that is bring into the system. And then you send back this force to the finite element model, and the finite element models do another iteration and realize that, wow, we went a lot too far. So let's back up. And when this happens, you just change the direction of the friction force. The friction is always opposed to the direction of movement. And then you just start oscillating in between all the iterations like this. And this was in all degree of freedom. And this was mainly observed when we activated the rotational part of the system. So what we did, we decided to characterize the friction itself. So pretty much we did cycle in all the directions. So pretty much what we were doing is we cycled into the X. We put everything into relative except for the Z, the vertical part, which is simply in force control. So we keep the actual load pretty much at the same level. And we stepwise incremented the load like this, either in tension or in compression. So we end up having a hysteresis loop that looked like this. So each of the levels that you see here is by increment of 500 kilonewton. I think this one was in tension. We did as well into compression, but as you can see here, this is the expected behavior of the specimen. And the stiffness of the system, like this one here, the stiffness of the friction and the specimen itself is 140 kilonewton when you start something. So the stiffness of the friction is way more higher than the specimen itself. So we did the characterization, and either when we were doing a free body diagram, either if we do it in X, Y, Z direction whatsoever, we always end up having pretty much the same slope here, either if you go into tension or in compression. So, but if the actuator is in tension, the slope is slightly, the friction is slightly higher than it is when it goes into compression, because the surface of contact is not the same into the swivels here. So with that model, we could end up having pretty much some kind of linear equation that we can put. In fact, we did more than this. We developed an open seas model that we put right now on the side of our specimen, inside the finite element model. So pretty much this model here represents the friction inside our model, in our lab. Okay, but it's modeled numerically within open seas. And the thing is that it is modeled, but it's not exactly the friction, it's completely the opposite. It's a negative stiffness, in fact, that we put there. So if you do a bad prediction and you put more compensation of friction, then you might end up having instability during your analysis because you're putting negative stiffness here. This was done by Ali Manpour. Another thing we had to put into the system is, Sean talked about it this morning. We used programmable channels into MTS, and we implemented some kind of smoothing function. So we still, even if we're correcting for friction and things like that, since the system is a PID and is always correct, okay, to get exactly at the position it has to be, so it just oscillates, but at very, very low level of forces. But still, we have those kind of oscillation appearing. So what we send back to the finite element model is not the oscillating part of the system, it's just a smoothing function. So that way, it reduces a lot the amplification or the oscillation during the test. But you have to use both systems at the same time. So you need the friction estimation and reduction into the open seas model, but you need as well the compensator or the smoothing function. You need both at the same time. Why? Here we just did a test where we don't have any open seas model for the negative friction. We only use the smoothing function. If you look at this test here, it was bridged here. We pretty much loaded with, I think it was a Loma Prieta earthquake, something like that. And what we have here is the force, sideways force, or the shear, in terms of times. When you compare this with the numerical prediction, and you compare your hybrid test in terms of force, both of systems are pretty much catching up. They're on top of each other. So you have a good correlation here. But when you look at the displacement level, what you find is that the hybrid response is way more lower in terms of amplitude compared to your numerical prediction. So what's happening here, friction is taking part of your energy here. So you have to take that into account. So if you put the friction reductor inside the model, then you're going to start having a way better correlation in between the two. We thought I had this idea of putting 64 load cells to measure real-time all the friction. I see someone's laughing. Yeah, it was quite expensive solution. No, not everyone was really believing that this would work, but I think that would have been the most effective solution. There's nothing like measuring something, so all the tests, the cyclic tests to characterize the friction, we did it, and we made a lot of assumptions. And we thought that all the vertical actuator swivel would react with the same level of friction, but we know that it's not the case. But still, we get a good control of it. It's not perfect, but I think that option would have been the best solution, but quite expensive. So the next step is to develop a new friction estimation. The problem with the open seas is that it is relying on the displacement of the specimen. So, but the Platon is pretty much referencing with the absolute referencing, not the relative one. So at first, we don't have a good correlation between the displacement of what is happening in the lab and inside the finite element model. Moreover, we cannot make the actual load vary into the system, into open seas, the friction compensator. So we want to use our real-time machine and to implement. This is the heuristic loop of the friction, the real one that we have in the lab. So we want to implement that into a Simulink, and it's going to pretty much do the 64 load cell stuff, but it's going to do it numerically on the side. So, and this machine would work all the time. It would not only work for hybrid testing, it would work as well for quasi-static or pseudodynamic or any other test that we want to do. So this is one thing that we intend to do in the near future. Measurement precision. Okay, so when the system was first delivered at Polytechnique, it was provided with the encoders. So these are the encoders that we use for the relative referencing. And the resolution of those encoders was 25 microns. We thought at the time it would be accurate enough, but when we inserted the very, very stiff specimen, concrete specimen, we ended up facing a major convergence problem. 25 microns for a specimen of that size represents about 20 kilonewtons in terms of axial load. But to activate the 25 microns, you have to move that 25 microns. So it's not all the encoders that moves at the same time. It's a triangulation. And triangulation use cosine, sine, and everything. So the numerical part is somehow polluted with some kind of imprecision due to this triangulation. And so pretty much we were not able to do any hybrid test on a stiff specimen. So at that time, that was the best resolution that was available. It's not that MTS was cheap, not at all. It's that they could not provide us with a better resolution. So pretty much we called the manufacturer, and they said that they have something that is 32 times more accurate. And that makes all the difference in the world. Even for a softer specimen, it really reduced the amplitude of the oscillation. One thing I didn't talk about is the backlash that there is into the swivel of the vertical actuators. You either have to decide if you allow backlash but minimum friction, or you allow no backlash and maximum friction. In our case, since friction was an issue and we don't correct it correctly, we decided, okay, let's live with backlash and have less friction. Okay. But when we're going to implement the finite element, not the finite element model, but when we're going to implement into the real-time machine the friction compensator, probably we're going to tighten them up and go to the maximum friction and less backlash. When you're using a relative system, sometimes you hear the solo valve opening and the system takes a kind of time to reach a certain level of displacement before it activates the relative system. So this is due pretty much to the backlash that is presented into the system. So having all these issues pretty much solved, then we did process to hybrid simulation testing. So what we're using is the OpenSeas software. The physical testing system is a FlexTest 200 controller from MTS and our maps, not the MDHTS. The middleware is OpenFresco, and pretty much we're using CSI from MTS. Sometimes we have used in the past the Simulink platform, but right now we just use the CSI configuration. So here's a first application. This is the concrete wall. So pretty much you see all the numerical part here. It's a 5-story building, and this concrete wall here was fabricated at Poly. It's about 4.5 meters high. It weighs 24 tons. The capacity of the crane is 25 tons, so hard to go bigger than this. And it represents a staircase pretty much. So it's an open section, and it's very hard to model in terms of torsion. So, and doing a 6 degree of freedom test onto this thing, I think it was a world premiere, if I can recall. So we did hybrid testing with this specimen, and we did it in November 2017, and the test lasts for 89 hours. So we start the test, and 4 days later, the test is done. You would say that we are really far away from real-time hybrid testing here. Okay. We need, with stiff specimen, you need high precision, but you need very low level of time stepping. Okay. And that was the reason why we end up having a very, very long test like this one. But it was a successful test, in fact. After the test, we did 2 major earthquakes with this. So we did a major earthquake, and then we did an aftershock. And after that, a student from Concordia University repaired a specimen with the fiber, carbon fiber, and we retested it. In fact, the last test was done yesterday, so I cannot present you the results, but it was a success. Okay, but the case here is not to show you any results or anything, it's just to show you that we were able to do it. So I show you the displacement in the X direction. It was an earthquake that was in both directions. So it was a full 6 degree of freedom system. So what you can see here in the red dotted line is the hybrid testing simulation, and the blue line is pretty much the numerical prediction. So the student did a great job, and as we can see, hybrid testing is really capturing or exactly what was the prediction, in fact. So it means that we had to use the friction model inside the OpenSeas as well as the smoothing function. Another test that we did was on multi-tier brace frame. So these are regular concentric brace frame. The difference is that there is no floor in between each of the braces. So it's pretty much you end up having a slender column. And this is pretty much what we did test in the lab. So the lower part of that column. So I have a video of this. So it's an accelerated video. The test lasts 50-something hours, I don't recall exactly. That was done in last December. So to repair the specimen, we did test the concrete specimen. We removed the specimen from the machine. It was repaired. In the meantime, we did that test, and then bring back the concrete specimen afterwards. You can imagine when you have this kind of equipment in a lab, the professors are piling up one after the other. They want to use this machine. Okay, so you cannot let this machine doing nothing for 3 or 4 weeks, forget it. Okay, so pretty much what you're going to see here is the axial load, so when it goes into positive direction, is in compression. And this here is the axial displacement for a positive value. It's shrinkage, pretty much. So it's a post-buckling prediction that we are doing here. I don't have the animation on the other side, however. So the objective here was to prove that there's a lack into the codes that is not well capturing multi-tier brace frame for the columns. So we could end up having the collapse of the building, and that was the case here. Okay, sorry about that. So in conclusion, at Polytechnique, we have a testing facility that is fully operational. We consider that fully operational now that we are able to do 6 degree of freedom tests on a stiff specimen. And is meant as well for large-scale structures. The test program were successfully done on a steel column and concrete structural members. Local displacement was mandatory for us, and it must be for anyone who is doing hybrid testing. Friction removal was the major challenge here and still remains that. So I know that Swinburne University wants to get rid of their friction as well. So we're going to work closely together to do that. And 6 degree of freedom hybrid simulation testing on stiff specimen is quite challenging, and it's very sensitive to your accuracy, so the noise level that you have in your system. If you have any errors that are inherent from the numerical part or from the physical testing equipment, and if you have resolution issues, if your load cells are noisy or they're not precise enough, then you're going to have really a hard time trying to get convergence. But a good way is to reduce time stepping a lot. So I'd like to thank UC Berkeley Peer for providing us OpenSeas and OpenFresco. It's a marvelous software, so we really enjoy using those. Very powerful. So without those software, we would not be able to do hybrid testing as we did at Polytechnique. We'd like to thank as well MTS system, especially thanks to Sean, who provide us a lot of helpful advices and help us a lot into the development of this system. Many thanks to many researchers and organizations in Canada. So, thank you for your attention.